Hello everybody, I'm A.McMahon and today I want to talk a little bit about X-ray diffraction and characterization methods for nanomaterials innovation. Through this presentation, I plan to cover an overview of nanomaterials, as well as X-ray diffraction techniques applied to nanomaterials with a focus on powder X-ray diffraction and a case study in which a nanomaterial is characterized via X-ray diffraction. Additionally, I want to talk about some other characterization methods, particularly microscopy and spectroscopy techniques, and quickly discuss these methods relating to innovations. So what are nanomaterials? Well, nanomaterials are materials found at the nanoscale, and they have features on the nanoscale, typically between 1 and 100 nanometers classically, and these can be external dimensions or internal structures or surface structures. They're often analyzed in bulk or as nanoparticles independently, but it should be noted that nanoparticles have significantly different properties when compared to their bulk counterparts. As such, there are multiple classifications of nanomaterials based on their dimensionality, morphology, composition, as well as their uniformity and agglomeration state. Of most importance here, particularly, is dimensionality. There are 4 dimensionalities with which nanomaterials can have. The first being zero-dimensional, where all dimensions externally are on the nanoscale. One-dimensional, where 2 external dimensions are on the nanoscale. Two-dimensional, where 1 external dimension is on the nanoscale. And then three-dimensional, where all dimensions on the external scale, externally are greater than the nanoscale. However, the material is composed of a nanocrystalline lattice or has nanoscale features internally or externally. And so this chart here just presents a few things, shows a few examples of nanostructured materials at different dimensionalities. So for example, zero-dimensional nanomaterials include solid, hollow, and core shell nanoparticles, quantum dots. One-dimensional includes things like carbon nanotubes and nanorods and nanowires. Two-dimensional includes things like graphene, metal carbides, metal nitrides. And three-dimensional includes things like graphene aerogel, crumpled graphene balls. So now I'm going to move into X-ray diffraction with regards to nanomaterials. And fundamentally, it's the same analysis as done on anything else. Same equipment, same methods, using a powder sample. There are some changes required to analytical methods after. However, it's generally still used to analyze external morphology, crystal phases, crystallite size, and microstrain. And phase identification is probably the most common application. However, there is a problem with significant peak broadening, such as shown here in this experiment where palladium nanoparticles were analyzed. And this happens because nanocrystals do not satisfy the ideal perfect infinite crystal assumption. And as such, difficulty with low intensity and very close peaks can occur. To offset this, photon counting data can be collected to help separate peak contributions, or more analytical methods such as the Rietveld method can model the entire diffractogram and allow you to better understand what's going on. And so X-ray diffraction is also able to determine crystallite size and microstrain. And crystallite size is determined using the Scherer equation, and the Rietveld method is typically employed to help with both because it simulates the experimental an experimental X-ray diffraction pattern with contributions from the atomic structure of the material, as well as the diffraction peak profiles that have already been generated. It uses other functions to help sort of smooth out the errors that occur because of the size of the nanocrystal particles. So in this study, nanocrystalline zirconia powder doped with the yttrium substance was observed, and the diffraction pattern shown to the right is for the calcinated powder with an assumed pseudofluoride tetragonal unit cell. Because of the size of the crystal, 004 and 400 peaks are actually split. And so a higher intensity peak was used to estimate the average size, in this case the 111 peak, and determined a grain diameter of 92 angstroms. Secondary estimates were also taken through this experiment, though, as shown in tables 5.1 and 5.2 on the right. And they use the Rietveld method and a pseudo-Voigt function to determine size, microstrain, lattice parameters, as well as peak breadths. A Williamson-Hall plot was also used, and after such analysis, a corrected Rietveld method with further accounting for instrumental effects was done, and the data presented in table 5.5 is actually the most accurate data because it takes into account the corrections from the Rietveld, from the Williamson-Hall plot, as well as the corrections for instrumental effects. And there are other variations of X-ray diffraction for characterization for nanomaterials. Small angle X-ray scattering is generally employed because it provides nanoscopic resolution and provides great structural information at that level. Additionally, it showcases structural parameters. Grazing incidence X-ray scattering is great for studying thin films in which nanomaterials have been grown because it avoids absorption of X-rays at the substrate. Anomalous or resonant small angle X-ray scattering is also employed a lot because it exploits dependence of atomic scattering with photon energy. This results in structural information from a given element rather than just the entire material. There are other characterization methods, though. Many of these other methods are dependent on the properties that you wish to observe, and many methods do complement each other. Characterizable entities or properties include things like crystal structure, optical properties, shape, elemental and chemical composition, bond structure, the list could go on. And in fact, I show a lot of that here in this table presented in an article that I read that shows that there are multiple characterization techniques suitable for different properties. The real concern is whether or not it is highly effective or accurate enough for the amount or size of particle or material you choose to characterize. So I personally wanted to look at microscopy and spectroscopy a little bit more because they assume the majority of characterization methods. And there's a variety of characterizable properties that are found within them. And they typically have the most developed equipment and techniques. So for microscopy, I wanted to look at transmission electron microscopy, scanning electron microscopy, and atomic force microscopy. And for spectroscopy, I plan to look at Fourier transform, infrared spectroscopy, as well as UV vis spectroscopy. So transmission electron microscopy is a direct imaging technique, just like any sort of microscopy, whether it be an optical microscope or anything else, and provides real space imaging. And it's actually able to show an atom distribution in a nanocrystal and on the surface of a material. Additionally, it is also able to provide atomic resolution lattice images, and you're able to obtain chemical information due to the spatial resolution of 1 nanometer or better, and this allows for direct chemistry identification in a nanocrystal. Also, full structural characterization of a nanoparticle is done and can be done through scanning and standard transmission electron microscopy. So transmission electron microscopy works based on by the image being created through the transmission of electrons through a sample. Essentially, the electron is beamed down through the specimen and then diffracted by the lattices within the sample. Then phase and amplitude changes occur due to electron-sample interaction and scattering. The waves in the same direction create a point over on the focal plane, and the image that's produced on the image plane is the result of the interference pattern between these scattered waves. Now, besides just imaging atoms, defects are also able to be imaged by high-resolution transmission electron microscopy, which essentially backs out a little bit more. So on the left here, we have some examples of atomic structures, or crystal structures of material. And as we go down, we're able to see how these structures are developed via transmission electron microscopy. And on the right, we're actually able to see through high resolution transmission electron microscopy the presence of twinning and stacking faults in, I believe, a sample of platinum. So scanning electron microscopy is fundamentally similar to transmission electron microscopy. And the images produced by detecting reflected or knocked off electrons. It's primarily used for structural observations and is a higher resolution, so it's a little bit more panned out. However, an interesting case is the use in nanomanipulation, where microtweezers and probes can be used to physically move and cut materials. So here on the right, we have a gap in a material and we have a nanowire, and the nanowire is being placed through the use of these probes to bridge the gap. The last microscopy technique I want to discuss is atomic force microscopy. And this microscopy technique actually uses a cantilever system with a probe to create a 3D topographical render of the material surface. And its operation basically functions on the characteristics of the probe, as well as interaction forces between the probe and the sample. The distance between the probe and sample can also affect the operation. Effectively, the probe grazes the surface. However, in some cases, it can stay a little bit further away, but as it gets closer, it is repelled by electron orbitals in both the probe material and the sample material. Atomic force microscopy can also be adapted to detect electronic effects. Electrostatic force microscopy essentially uses the same probe and cantilever setup. However, it detects electrical field gradients between probe and the sample. A voltage can actually be applied to induce a field, which improves image contrast and is able to observe charge distribution as well as estimate surface conductivity. As such, it's also able to distinguish charges in insulating and conducting regions of a material. So as we can see here on the right, we have the probe scanning along the surface. It is able to determine and create two different renders, one showing the topography of the surface and another showing the electric field of the material. Next, we're going to talk about some spectroscopy methods. So Fourier transform infrared spectroscopy is based on the absorption of mid-infrared EM radiation. And if a molecule is able to absorb this infrared radiation, then the dipole of the molecules are modified and the molecules become IR active. And we can record this activity and create a spectrum of bands that are able to identify things such as bond strength, the nature of bonds, and functional groups. Similarly, in UV-Vis, ultraviolet visible light spectroscopy, we're able to determine similar things, and this is a very low-cost method that is able to measure the intensity of light reflected from the sample through the exploitation of optical properties near the particle surface. However, it is sensitive to size, shape, concentration, and agglomeration rate of particles. So now I want to talk a little bit more about the conclusions that I'm able to draw from this. So the first is that characterization is a process. Characterization is not a one thing. It's not just one thing that we can do. And there's a lot of things that have to be done to fully and comprehensively characterize a material. The next is that the techniques that we use are generally adapted from macro scale, and macro scale techniques don't always downscale well to the nano level. And as such, many techniques are only able to characterize specific traits and properties. From this, we've been able to determine that X-ray diffraction is a viable, although lengthy and somewhat more complicated technique than usual for structural characterization of nanomaterials. Microscopy techniques are more commonly used, and they are viable for structural characterization as well as some chemical characterization. And spectroscopy techniques can provide very useful information about composition and chemistry. However, thinking about innovation, it's clear that innovation is slowed within this industry by the lack of a one-stop shop method for complete characterization. While no real method exists for all materials, it is important to think about how we approach more holistic characterization of nanomaterials going forward to speed up the development and to produce more exciting and useful nanoscale innovations going forward. So with that, I want to say thank you very much, and I hope you enjoyed.